Welcome to another class of process heat transfer. In this lecture, I will talk about the radiation intensity. So the radiation is emitted by all parts of a plane surface in all the directions into a hemisphere above the surface from which the radiations are emitting. And the directional distribution of emitted radiation is usually not uniform in case of real surfaces, while in case of black body radiations, the directional distribution of the emitted radiations are uniform, but in case of real body this is not uniform. Therefore, we need a quantity that describes the magnitude of radiations emitted or incident in a specified direction in the space. So that's why we have to mention that the radiation intensity, and this quantity radiation intensity is represented by I, right? Before we can describe a directional quantity, we need to specify the directions of the emitted radiations in the space. The direction of radiation passing through a point is best described in spherical coordinates in terms of zenith angle, and this is a zenith angle, and this is a radiation which is emitted out from a point on a particular plane having the area dA, and this angle is called the zenith angle, which is the angle between the z direction and the center of emitted radiation. And the second angle, which is called the azimuth angle, which is the angle between the x-axis and the dotted line or the shaded line which lies on the xy plane. So this is the xy plane, which is basically a horizontal place or the horizontal surface. So this directional radiation has a shadow over here. So the angle between x-axis and this shadow is called the azimuth angle, as you can see in this diagram. So the radiation intensity is used to describe that how emitted radiations varies with the zenith and the azimuth angle. So the purpose of studying this topic is to see that the emitted radiation varies based on these angles in the spherical coordinates. If all the surfaces emitted radiations uniformly in all the directions, then the emissive power would be sufficient to quantify the radiation process, and we would not need any kind of intensity in order to describe the radiation. So this is not the real case always. So the radiation is emitted in a non-uniform manner in all the directions. So that is why we need to identify the radiation intensity. And what is the radiation intensity? It is the variation of the emitted radiation with these two angles. So in case of black body radiations, we know that from the black body radiations, the radiations emitted uniformly in all the directions. So the radiations emitted by a black body per unit normal area is actually the same in all the directions, and there is no need of the directional dependence that can describe the emitted radiations from the black body. So in the opposite, if we have a real surface and we need to specify the directional dependence, and we also need to specify the size of the opening through which the radiations are basically emitted, and in case of real surfaces we need to specify this size from where the radiations are being emitted, and we need to define the intensity in case of real surfaces. So This is all about if we are describing the emitted radiation in case of real surfaces. Now let's discuss the next topic, that is known as the radiative properties of the materials. So most of the materials that we encountered in practice, they could be metals, woods and bricks. They are actually opaque to thermal radiations, and radiation is considered to be a surface phenomena for such kind of materials. So thermal radiation is emitted or absorbed within the first few microns of the surface. So we speak of the radiative properties of surfaces for the opaque materials. So those materials which are not transparent, so we only consider the surface radiations or the radiative properties only on for the surfaces for such kind of non-transparent or opaque materials. On the other hand, we have some other kind of materials such as glass, water, which will allow the visible radiations to penetrate to a considerable depth before any significant absorption takes place. So the radiation through such kind of materials, sometimes also called the transparent materials, obviously cannot be considered to be a surface phenomena, since the entire volume of the material interacts with the radiations. So the materials such as glass and water, which are semi-transparent to visible radiation, but at the same time they are considered as opaque materials for the infrared radiations. So it depends on the incident radiation. So for the visible light, glass and water are considered as semi-transparent. So a part of the radiation is being absorbed, and in case of infrared radiation, so the glass and water are considered as opaque materials. So materials can exhibit different behavior at different wavelengths, and the dependence on the wavelength is an important consideration in the study of radiative properties. So the radiative properties are known as the emissivity, absorptivity and reflectivity and transmittivity of the material. We will discuss all these radiative properties such as emissivity, absorptivity, reflectivity and transmittivity in the upcoming slide. So a black body, we have already studied about the black body. So we know that a black body is a perfect absorber or the perfect emitter of radiation. So nobody can emit the more radiations than a black body at the same temperature. So what we consider is, we consider the black body as the reference material for describing the emission and the absorption characteristics, and when we compare it with the real surfaces. Now let's discuss about the emissivity. That is actually one of the radiative property. So what is emissivity? The emissivity of a surface represents a ratio of the radiation emitted by a real surface at the given temperature to the radiation emitted by the black body at the same temperature. So it is simply a ratio in which on the upper side of the ratio will take the radiations emitted by a particular real body at the same temperature divided by the radiations emitted by the black body at the same temperature. So emissivity of a surface is normally represented by epsilon, and it always varies from 0 to 1. So it may be either 0 and it may be either 1, and the values always lies in between 0 to 1, and there will always be a fractional value between 0 to 1. It may be 0.1, 0.5, 0.7, etc. So the emissivity is actually a measure of how closely a surface approximates a black body. So for a black body, the emissivity would usually be equal to 1. The emissivity of a real surface is not always a constant quantity. Rather, it varies with the temperature of the surface as well as the wavelength and the direction of the emitted radiation. So the different emissivities can be defined for a surface depending upon the effects that I have discussed earlier may be considered. The effects may be temperature, maybe the wavelength, and maybe the direction of the emitted radiation. The most elemental emissivity of a surface at a given temperature is known as the spectral directional emissivity. So this is actually the formula of the spectral directional emissivity. So emissivity is the ratio of the radiations emitted by a real surface, right, and the radiations emitted by the black body, right, or the radiation intensity by the real surface and the radiation intensity by the black body. So it can also be defined as the ratio of the intensity of radiation emitted by a surface at the specified wavelength in a specified direction to the intensity of radiation emitted by a black body at the same temperature at the same wavelength. So in case of real surface, we have to consider the wavelength and the directions in the spherical coordinates, right? So these are the coordinates that I have already discussed, and this is the temperature dependence. While in case of the black body, we do not need any kind of directional dependence. So here these subscripts are called the wavelength, and these quantities that theta and the phi, which are used to designate the spectral and the directional quantities of the radiation intensity from the real surface. So the black body radiation intensity is independent of the direction, as I have said earlier that there is no need of the directional dependence in case of the black body radiation. So this is the formula for the spectral directional emissivity, in which we compare the emissivity, the emitted radiation of a real body with the black body. Let us discuss about the absorptivity and reflectivity and transmittivity. So everything around us constantly emits radiations, and the emissivity represents the emission characteristics of the bodies which are around us. So this means that every body, including our own body, is constantly bombarded by the radiations coming from all the directions over a particular range of wavelength. So the radiation flux is a particular quantity which is actually represented by this G, and if in case of the radiation flux for the incident radiation on a particular surface, that is simply called the irradiation and simply represented by this G, right? So consider this is a particular surface, and if the radiations is coming on this surface, so the incident radiation is falling on this surface, so we will simply say that this is irradiation, and this is called the radiation flux, right? And it is represented by G, and it can be simply understood by this diagram, right? I will come to this diagram later, that if this is the incident radiation and the flux will be watt per meter square, and the part of the incident radiation is being transmitted, is being passed through this semi-transparent material. So we will say that let's say the incident radiation is coming onto this surface, and the 25% of the radiation, incoming radiation, is passing through or transmitting through the surface. So we will say that a part of this incident radiation flux will be passing through this semi-transparent material, and a part of this incident radiations are being absorbed by this semi-transparent material, and a part of this incident radiation will be reflected back in another direction. So the reflected back radiations will move away in a certain angle or in a certain direction, and it always depends upon the angle of incident and the surface properties of the materials. It also depends upon many other parameters. So here we are just trying to understand that. So if we have a semi-transparent material and the radiation is coming, so what will gonna happen, that a part of the radiation will transmit and the part of the radiation will be absorbed, and the part of the radiation will be reflected back into the atmosphere. So based on the diagram, this diagram that I have shown you, so we can just define that the fraction of the irradiation absorbed by a particular surface is called the absorptivity, and the fraction of reflected fraction of radiation is reflected by the surface is called the reflectivity, and the fraction of incident radiation is being transmitted through the surface is called the transmittivity. And the absorptivity is represented by alpha, and the reflectivity is represented by rho, and the transmittivity is represented by tau. Do not confuse this tau with the shear stress or the wall shear stress that we have studied earlier. So the absorptivity is the ratio of the absorbed radiation divided by the incident radiation. So the ratio is always less than 1, right? Less than 1. So it means that if the incident radiation is coming on the surface, a part of this radiation will be absorbed. Obviously, let's suppose if we say that the incident radiation is equal to 100 and only the 20% of the radiation are being absorbed. So if we write down 20 over here and divide it by 100, so it means that this ratio would be equal to 0.2. So it means that the 20% of the incident radiation are being absorbed by that particular semi-transparent material. And similarly, we have to define that the reflectivity is the ratio of the reflected radiation divided by the incident radiation. So this is the radiation flux of the reflected radiations divided by the flux of the incident radiation. So it also varies from 0 to 1, and on the similar grounds, so the transmittivity is the ratio of the radiations are being transmitted through the surface divided by the incident radiations. So it is also the ratio of the transmitted radiation flux divided by the incident radiation flux. So it also varies from 0 to 1. So this is all about the absorptivity and reflectivity and transmittivity. So from the first law of thermodynamics requires that the sum of the absorbed and the reflected and the transmitted radiation energy would be equal to the incident radiation. So this is the definition of the first law of thermodynamics, and if we put the value over here, or simply if we can divide this G on the left hand side, so this will be G absorbed divided by G, which is known as absorptivity. This is G radiation reflectivity divided by G, which will be known as the reflectivity. And if this GTR, which is known as the flux by the transmitted radiation divided by the incident radiation G, which is known as the transmittivity. So from this definition of the first law of thermodynamics, we have developed an expression which shows that the absorptivity, reflectivity and the transmittivity for a semi-transparent material would be equal to 1. So in case of this expression is useful for only transparent material, where the transmittivity, absorptivity and the reflectivity phenomena are taking place. Whereas in case of opaque surfaces are those surfaces through which the light cannot be transmitted. So for the opaque surfaces, we can say that the transmittivity would be equal to 0, and if we put transmittivity equal to 0 in this equation, we will have the new expression for the opaque surfaces, in which we can say that the absorptivity and the reflectivity would be equal to 1. This expression is for the semi-transparent material, and this expression is for the opaque surfaces where the transmittivity equal to 0, and the final expression would be alpha plus rho would be equal to 1. This next topic of this lecture is the radiation heat transfer through diffuse and the gray surfaces. So the analysis of the radiation heat transfer in enclosure consisting of black surfaces is relatively easy, and in most of the cases we encountered in practice involves the non-black surfaces, which are not really black, so which allows the multiple reflections to occur. So the radiation analysis of such surfaces becomes very complicated until or unless some simplifying assumptions are being made. So to make this phenomena, or to make this topic more easier, so we'll take a simple radiation analysis that it is common to assume the surfaces of the enclosure to be opaque, diffuse or gray. That is, the surfaces are non-transparent and they are diffuse emitters or the diffuse reflectors, and their radiation properties are independent of the wavelength. Also, each surface of the enclosure is isothermal, and the both incoming and outgoing radiations are uniform over each surface. For this, we will discuss the first topic, that is known as the radiosity. What is the radiosity? To understand the radiosity, that first of all, let us consider the surfaces emit radiation as well as reflected, and the radiations leaving a surface consist of emitted as well as the reflected parts. So the calculation of the radiation heat transfer between the surfaces involves the total radiation's energy streaming away from the surface with no regards of its origin. So the definition of the radiosity is that total radiation energy leaving a surface per unit time per unit area is called the radiosity, and which is simply represented by this J, right? So simply once I will repeat again, the total radiation energy leaving a surface per unit time per unit surface area is called the radiosity, and it is represented by J, right? Let us have some derivation or some formulas to understand better about the radiosity. So consider a surface I which is gray and opaque. Let's suppose this is a surface and it is represented by I, and it is gray and opaque, and we have just said in the previous slide that for the opaque and the gray surfaces the transmittivity is equal to 0. So the equation would become absorptivity plus the reflectivity is equal to 1, right? And in this case the emissivity would be equal to the absorptivity. So the radiosity can be expressed for this surface and by this formula. So what I have said earlier, that the radiosity is the total energy leaving a surface per unit time per unit area. So this is the incident radiation G which is coming onto this surface. So for the determination of the radiosity, we have to take into account the total energy leaving a surface per unit time per unit area. So the energy leaving from this surface in case of two ways. The one is by the reflected radiation and one is by the emitted radiation. So the reflected radiation is represented by the reflectivity multiplied by its reflective flux, right? And the emitted radiations is represented by the emissivity and multiplied by the EB, which is known as the emittive power or the emissive power, right? So this is the formula for the radiosity. Ji is equal to the radiations emitted by the surface plus the radiations reflected by the surface. So we have to take into account the reflected part as well as the emitted part. So the radiations emitted by the surface is known as can be represented by the epsilon multiplied by the emissive power plus the radiations reflected by the particular surface I is represented by the reflectivity and plus its reflective flux. So this is the second equation. It's the first equation. The second equation, in this equation we can just replace this reflectivity with 1 minus epsilon. How? So in this equation we can replace this alpha, the absorptivity, with the emissivity, and after rearranging this equation we can replace this reflectivity with 1 minus epsilon. This is the final expression for the radiosity, which incorporates the radiations emitted by the surface and the radiations reflected by a particular surface I. So we have studied earlier that the black body emissive power is equal to the Stephen-Boltzmann constant into the temperature to the power 4. Temperature must be in absolute scale. Is the black body emissive power of a surface I, where Gi is the irradiation or the incident radiation, and the radiation energy incident on a surface per unit time per unit area. So for a surface which can be approximated as a black body, and for the black body we have said earlier that the emissivity would be equal to 1. So the radiosity relationship reduces to this expression only that we have said earlier. How? If this is a black body, right? If this is a black body, so the emissivity would be equal to 1. If we put 1 over here, so 1 minus 1 would be cancelled out, and if we put 1 over here, so the radiosity would be equal to the black body emissive power. Same is the case over here. The radiosity would be equal to the black body emissive power if we put the epsilon, which is known as the emissivity, equal to 1 in the previous expression, and we will have this expression after simplifying that. And we have already know that this expression, and we have already studied the formula related to the black body emissive power, which is equal to the multiplication of Stephen-Boltzmann constant into the temperature to the power 4. The radiosity, this is a very important statement that you need to keep in mind, that the radiosity of a black body is equal to its emissive power. This is only applicable for the black body, and this is expected since a black body does not reflect any kind of radiation, and the radiations coming from a black body is due to only by the emission. So the reflected part would be cancelled out if we put the epsilon, or the emissivity would be equal to 1. In this topic I will talk about the net radiation heat transfer to or from a surface. So during the radiation interaction, a surface may lose energy by emitting some radiations, or may gains a part of the energy by absorbing the radiation emitted by other surfaces. So a surface experiences a net gain or a net loss of energy depending upon which quantity is larger. If it is gaining energy, so it means that so the net gain would be higher. If a particular surface is losing some sort of energy, so the net loss would be higher. So the net rate of radiation heat transfer from a particular surface I of a surface area AI is denoted by the QI. This is the net rate of radiation heat transfer, and it could be expressed by this equation that the net rate of radiation heat transfer, this subscript I stands for any particular surface. So the radiations leaving the entire surface I minus the radiation incident on the entire surface I. So this part of this equation, so this is the equation. So the first part of the equation, the radiation leaving the entire surface. So we have just developed the expression for this part, which is known as the radiosity, right? So the radiosity is the net rate of radiation leaving from a surface per unit area per unit time. So for this part we can just denote it by the Ji, which is known as the radiosity, and this is the radiation incident on the entire surface I, and it is represented by the Gi, which is also known as the irradiation or the radiation flux, right? So both of these quantities, the radiosity and the radiation flux, can be represented by the radiation per unit area and per unit time. So if we multiply the area of the entire surface, right, from both of these two terms, so we will have the units of the rate of net rate of radiation heat transfer. So if we have any surface which have a surface area I, after multiplying it we will get this QI, which is the net rate of radiation heat transfer. So this is the first formula, and we have just put down the values, and we will have this second expression. It has a unit of watts. So what we will do next is we will put the values of Gi in this expression, and the value of the Gi can be taken from the previous slide. I will go there in few seconds. So let me just rewrite this equation, this second equation, into this form. So Qi will be same as it is, and Ai will be same as it is, and the radiosity will be same as it is, right? So where this Gi comes from, if you go backside, right, and we have just studied this expression for the radiosity, right? We have just studied the expression for the radiosity. So Ji is equal to this expression, and if we take the Gi on one hand side and take all the parameters on the other hand side, so what would be equal to? Gi would be equal to Ji minus this expression divided by 1 minus epsilon. So we can put the value of G from our previous slide and put it over here, right? And after simplifying that, we will have this expression. Let me just go to the next slide. So this is the same expression that I have mentioned in the previous slide. So after putting the value of Gi, that is the radiation flux, and after simplifying that, we will have this expression. So this is the constant terminology, and this, if we rearrange this expression, right, Ai and epsilon can be taken over this value, that is 1 minus epsilon over r, as I have mentioned over here, and this could be represented by the resistance of that particular surface I, right? So this expression can be converted by this expression if we replace this part of the equation with the resistance of that surface. So the resistance of that particular surface can be represented by this formula. This equation is known as the surface resistance to radiation, and in this equation the quantity, the emissive power and minus the radiosity correspond to the potential difference, and the net rate of radiation heat transfer corresponds to the current in the electrical analogy. The direction of the net radiation heat transfer from this equation depends upon the relative magnitudes of this value, which is known as the emissive power of a black body at the temperature of the given surface, and the radiosity of that particular surface. So if the value of this emissive black body, emissive power of a black body is higher than this Ji, if this Ebi is greater than this Ji, then the radiation heat transfer from the surface would be considered. On the other hand, if this parameter would be high and compared to this one, so the radiation heat transfer would be to the surface. So we can just say that from this equation. So in this equation there are two parameters, that the emissive power of a black body and the radiosity. And if the emissive power of a black body would be greater than the radiosity, then the radiation heat transfer from the surface, and if the radiosity is greater than the emissive power of a black body, then the radiation heat transfer to the surface. A negative value of the Q, in this case we will see that a negative value of the Qi, that the heat transfer is to the surface, and all of this radiation energy gained must be removed from the other side of the surface through some sort of mechanism if the surface temperature is to remain constant. The surface resistance to radiation of a black body is 0, since the emissivity would be equal to 1 in case of the black body, and and the emissive power of a black body and the radiosity would be equal in case of the black body. We have just studied this earlier in the earlier slide, that if we have a black body, and in case of black body the radiosity and the emissive power of black body would be equal to 0, and the radiation resistance would also be equal to 0 in case of emissivity would be equal to 1. If we put the emissivity would be equal to 1 right over here, so this resistance would be equal to 0. In the topic that is the simultaneous heat transfer, and I will discuss about the three different modes of heat transfer, how it could be occur simultaneously. So we have mentioned that there are three mechanisms or the modes of heat transfer, but not all these three mechanisms can exist simultaneously in a medium. For example, the heat transfer is only by the conduction process in the opaque solids, but the heat transfer might be occur by the conduction and the radiation in the semi-transparent solids. Thus, a solid may involve the conduction and the radiation, but in solids we cannot see any kind of convection. A solid may involve the heat transfer by the convection or the radiation only its surfaces exposed to the fluid or to other surfaces. For example, the outer surface of a cold piece of a rock will warm up in the warmer environment as the result of the heat gained by the convection process or from the air, and the radiation from the sun and the warmer surrounding surfaces. But the inner parts of the rock will warm up as this heat is transferred from the outer surface to the inner region of the rock only by the conduction process. So the heat transfer is by the conduction or by the radiation if the fluid is still, that means there is no bulk fluid motion. So in a bulk fluid motion, the heat transfer can be occurred by the convection and the radiation if the fluid is in motion. So there are two cases, that the first is the fluid is in still motion, and the second case is the fluid is moving. If the fluid is in still motion, the heat transfer can be occurred by the conduction and possibly by the radiation, and if the fluid is moving, the heat transfer might be occurred by the convection and the radiation process. In the absence of the radiation, the heat transfer through a fluid is either by the conduction, convection, and depending upon the presence of any bulk fluid motion. Convection can be viewed as the combined conduction and the fluid motion, and conduction can be viewed as the special case of convection in the absence of any fluid motion. So finally, we can say that when we deal with the heat transfer through a fluid, we have either conduction or convection, but not the both cases. Also, gases are practically transparent to the radiation, except that some gases are known to absorb radiation strongly at certain wavelengths, such as ozone, for example, strongly absorbs the ultraviolet radiations. But in most cases, a gas between two solid surfaces does not interfere with the radiation and acts actively as a vacuum. So the liquids, on the other hand, are usually strong absorber of the radiations. Finally, the heat transfer through a vacuum is only by the radiation process, since the conduction and the convection requires the presence of the particular medium. Let's take an example of the heat loss from a person. Let me just read the question statement first. That consider a person standing in a breezy room at the 20 degrees centigrade. What does it mean? The air inside the room is moving, right? So determine the total rate of heat transfer. Determine the total rate of heat transfer from this person if the exposed surface area and the average outer surface temperature of the person are 1.6 meter square is the surface area and 29 degrees centigrade is the body temperature of this person. And the convection heat transfer coefficient is given as 6 watt per meter square per degree centigrade, as you can see in this diagram. So this is a person standing inside a room, and the room temperature is 20 degrees centigrade and the person temperature is 29 degrees centigrade, and the heat is basically transferred from the higher temperature to the lower temperature. So there might be the two phenomena of the heat transfer. The one is by the convection process, and we are given with the convective heat transfer coefficient, and the second is by the radiation process. So the heat transfer by these two phenomena are going to take place in this room. So we have to determine the total rate of heat transfer, including by the convection process and the radiation process. Let's have a look on the solution of this problem. That we have to determine the total rate of heat transfer from a person by both convection and the radiation to the surrounding air, and the surfaces are specified temperature is to be determined. So we'll take few assumptions that the steady operating conditions exist because the temperatures are given here and it doesn't change with time. So the person is completely surrounded by the interior surfaces of the room. So we know that the person is inside the room and the surrounding surfaces are at the same temperature as the air in the room. So the room inside the air and the inner walls of the room are at the same temperature, that is at 20 degrees centigrade. So the fourth one is the heat conduction to the floor through the feet is negligible because very small area of that person is in contact with the floor. So that's why because of the very limited area is in contact with the floor, so that's why we can neglect the heat conduction from the person to the floor. So the properties that we are going to need is the emissivity of a particular person, and it can be taken from the book that I have already told you from table 1 into 6, and the emissivity of a person can be taken as 0.95. So in the analysis, the heat transfer between a person and the air in the room will be by the convection instead of conduction, since it is conceivable that the air in the vicinity of the skin or the clothing will warm up and rise as a result of the heat transfer from the body, so initiating the natural convection currents. So it appears that the experimentally determined values for the rate of convection heat transfer in the case of 6 watt per unit surface area per unit temperature difference between the person and the air away from the person. So the rate of convection heat transfer from that person can be determined by this Newton's law of cooling, and we already know that the formula of the Newton's law of cooling, and the convective heat transfer rate will be equal to the convection heat transfer coefficient multiplied by the surface area, the surface temperature, that is the person temperature, and that is T infinity, which is the temperature far away from the object or far away from the person. So this is 20 degrees centigrade. So the convection heat transfer is 6, and the surface area of that particular person is also given, that is 1.6 and meter square, and the temperatures are also given, the person temperature and the room temperature. So after putting the values, we can just get the value of the convection heat transfer rate, that will be equal to 86.4 watts. So the second case is we have to determine the radiation heat transfer. So the person will also lose the heat by the radiation to the surrounding wall surfaces. So we take the temperature of the surfaces of the wall, ceiling and the floor to be equal to the room air temperature in the case of, for the simplicity. But we recognize that person does not need to be the case, and the surfaces may be at the higher or the lower temperature than that the average temperature of the air inside the room, depending upon the outer conditions and the structure of the walls. So considering that this aspect, that the air does not intervene with the radiation and the person is completely enclosed by the surrounding surfaces, the net rate of radiation heat transfer from the person to the surrounding wall inside the room and ceiling and the floor is given by this famous formula, that is Stephan-Boltzmann law. And this is the Stephan-Boltzmann law, and the emissivity can be taken from the literature, and the Stephan-Boltzmann constant value can also be taken from the literature, and the surface area of that particular person is given, and this is the surface surface temperature of the person inside the room, and this is the surrounding temperature, or everything is given. But keep in mind that this Stephan-Boltzmann constant has the unit of in Kelvin, so you must convert the temperatures in Kelvin, so by adding 273, and after simplifying that, the radiation heat transfer will be equal to 81.7. so in the question statement that it was being asked that determine the total rate of heat transfer. So the total rate of heat transfer could be determined by adding the convection rate of heat transfer and the radiation heat transfer. So it would be equal to the total rate of heat transfer from the body is determined by adding these two quantities, and that will be equivalent to 168.1 watts.